Welcome. At this time of the year we would usually be in the Swiss mountains, and at the end of summer I usually do some maybe more crazy stuff, and today I want to present something which is half-baked. It's something I like to think about on and off. It's a very interesting theme. How do you incorporate continuum notions into the discrete? And today I want to talk about the problem how to do symplectic geometry on finite graphs. So symplectic geometry was always a favorite topic of mine since as a sophomore I took a course by Jörg Fröhlich on mechanics, which was based on Sommerfeld's book or Arnold's book, which became my Bible. Arnold's book then has a lot of appendices which contains a lot of interesting questions, and one of them is the Arnold conjectures, which then kind of blew up at the time when I was a grad student. And that was also the time when this book came out of Hofer and Zehnder, and it was an exciting time. Fleur was visiting ETH, and I was in the same office and some of these symplectic guys, some of these Zehnder students, and could see kind of how it is when a grad student has to be near a giant. I was glad to be maybe on the shoulders of giants, but not have to compete with giants. But this topic has then exploded in the last 30 years, and it's a very interesting part of geometry. Symplectic geometry is kind of a little bit surprising sometimes, like these squeezing theorems, which are treated in this book show. Now the question is, what can we do on finite graphs? So this is a finite simple graph, and I just want to try and kind of also organize my thoughts a little bit by presenting this. So this is unrehearsed and maybe a little bit rough. But I want to start with the notion of what is a symplectic graph. So I like to keep things simple, and finite simple graphs are simple objects. So we take G is V, it's a finite simple graph. Now, such an object has already quite a rich structure. It has the Whitney complex, it has differential forms, it has Hodge theory, it has all kind of things. Once you have an exterior derivative, you can do a lot of physics. You can do electromagnetism, you can do gravity, you can do a lot of things. So what we have is an exterior derivative on this. And what is a symplectic graph? It's very simple. It's just given by a closed 2 form, which is nowhere 0. So let's see. So that's very simple. A 2 form is just a function on triangles, so that if you change the orientation of the triangle, then the sign changes. So that's differential forms are extremely simple to deal with on finite simple graphs, or simplicial complexes. But we always just take the simplicial complex, the Whitney complex. So that's a very kind of simple thing. So the only thing we really need until now is a triangle. If you have a triangle, we can already define a symplectic graph. And now the problem is, what are symplectomorphisms? So that's kind of a tricky question, because we don't just want to look at graph automorphisms and to have kind of some the omega preserved. Graph automorphisms are rare in general. If you take a generic graph, the automorphism group is the trivial group. So that's not so rich. But what we want to do is we want to have a notion which is close to the notion in the continuum, and also allows us to ask similar questions like in the continuum, like the Arnold questions about the number of periodic orbit or number of fixed points of a symplectomorphism. So it's tricky to define symplectomorphism, but in this book, I think that's probably the place where this really became popular. You don't look at symplectomorphism, but at symplectic Hamiltonian maps, which are obtained by time 1 maps of Hamiltonian systems. Now the question is, what is a Hamiltonian flow? And I thought about this for many years. So what do you want to do? You want to define kind of something like a discrete a rule which tells you from which node you go to which other node, or all kind of thing. That all doesn't work. Is unnatural in the sense that you can do a lot of different choices. It's like the theory of cellular automata of Wolfram is something which is very rich, very nice, very beautiful, but there are so many different rules you can consider. So there's nothing really natural. So that's kind of one of the difficulties with a theory which is too rich, is that you want to have something natural. But fortunately what happens is that nature already gives us the hint how to define this. If you look at the particle moving, even a spacecraft going to Mars, what happens is these are actually waves. These are not particles are waves according to de Broglie, right? So you have fundamentally on a quantum level, you actually look just at wave equations. So the right thing to do is on a discrete structure is to actually look at wave equations or wave type equations, and you can bend that, and that will come to Cartan's calculus actually allows you also to generalize waves to Lie derivatives of flows, and that mechanism and that formalism works very well on graphs, and I pointed that out in 2018. Also pointed out that the McKean-Singer works nicely there, generalizes. It's kind of just an observation, but that's actually important because we will see that then we can, if we have solutions to the wave equation, we have actually complex solutions of the Dirac equations, which is quite an interesting thing because the eigenvalues come in pairs. So that's kind of an interesting thing. So so we are in number 1. We have finished number 1, and I want to actually just look at the Cartan's magic. So first of all, we have an exterior derivative. And if you have an exterior derivative, you can look at the Hodge Laplacian. So this exterior derivative works on differential forms. So in this case, it's just a finite dimensional vector space with a number of simplices as dimension. So that's what you have. So the 0 forms are functions on vertices, the 1 forms are functions on edges, the 2 forms are functions on triangles, the 3 forms are functions on tetrahedra, etc., etc. So that happens when the D maps K forms to K+1 forms, and then we have the adjoint. And then we have the L. It's the Dirac operator. What is very nice in the discrete, you don't need any Dirac matrices or anything. You don't have to build up this Clifford structure because it's already built in. So that's already there. So you have that. So you have actually the Laplacian, this Hodge Laplacian. This Hodge Laplacian L has already a natural square root, and so you can for example look at the wave equation. So the spectrum of this, of course, L, 0 dimension of the kernel of L. It's B. It's the sum of the Betti numbers. These are Betti numbers. So this Hodge Laplacian has this block form. So this is L, L0, L1, L2. The kernel of Lk is the K's Betti number. And so this is the wave equation. And because it's d square, you can immediately, this is D'Alembert. you can immediately just write down the solution of the wave equations. So you check that this is actually working. And here this d minus 1, d is not invertible, but you can, this is the pseudo-inverse. So it has to be, the initial velocity has to be perpendicular to the harmonic forms. So the kernel. And that's actually the Arnold question, or the weak form which Fleur proved, is that there are at least as many periodic solutions of a, any of a symplectic map than this B here, or stronger the number of minimal number of critical points, which is not yet proven. But this version with B, with the number of the sum of the Betti numbers, that has a dimension of the harmonic forms, that has been proven. And so we tried to actually see what can we do in the discrete here with these things. So this is the D'Alembert solution, and actually you can actually write this also as, so if you take e to the, so if you take psi is equal to u0, I might have some signs wrong, plus or minus I u prime 0. Then c prime is equal to, that's just about the wave equation, which is actually just a Schrödinger equation. So what you have is actually just, you have quantum mechanics, wave. But these are ordinary differential equations. These are ODEs. With as many variables as you have simplices. So you can write them down directly. You can now look at vector fields. So what is a vector field? So this is given by an inner derivative. They naturally form a Lie algebra, and so what you have is actually you can look at the analog of this Hodge Laplacian. So this is the Lie derivative. So Lx is equal to d Ix plus d. And so you can write this as d plus Ix squared. So you see what happened was the d star in the wave equation went just to Ix, which allows you to do a more directed flow. So that's the, but that's just the Lie algebra. So you have a Lie algebra structure by just taking the commutator. We have to look at the notion of how do we define a symplectomorphism. So we have to kind of bring in this two form here. So there are various ways how you can describe Hamiltonian dynamical systems. That's kind of a beautiful one, but this is an almost complex structure. The modern way, which this also appears in this book, and which is kind of a more natural, is you just say that Ix omega is equal to dh. So that has to be exact. This inner derivative of this symplectic form has to be exact. And then so H is the Hamiltonian. In the discrete, there's still quite a bit of freedom to choose Ix, and so I think this has to still be investigated. Especially, we want them to look at this. We are very interested also in the spectrum. We will see the spectrum plays an important role. What happens with the spectrum? What happens with the eigenvalues, the zero eigenvalues in particular here, when you move from d star to Ix? And if all of them would move in the same way and become positive eigenvalues, then you would actually have the Arnold conjecture in the discrete? So that's kind of an interesting question. But there is still a little bit of uncertainty how general this can be, and also maybe how restrictive this is. In general, we didn't make any assumption on the structure of the graph yet, except that it has to have a triangle, so that we can define a two-form, so that we have a two-form. But that's kind of the key to define things. So if we have that, if we have a vector field which satisfies this, we call this the Hamiltonian, so then the flow, the Hamiltonian flow, it's just exactly the same thing then, but we just UTT is equal to minus LXC. Now there are difficulties here, so note that Lx is in general not self-adjoint. And so the spectrum can be, complex. It can have complex spectrum. So it's not so clear what actually the dynamics is. But what it is, it's kind of it just gives you classically. It gives you the solution of the Hamiltonian. So it's the analog of the continuum. So the time T map. Now there is also, for the wave equation, you have always an initial position and an initial velocity. But fortunately there is this McKean-Singer symmetry, which I in 2018 just realized that this also works for Lx, because the Dirac operator gives you so this D which you have is actually this D. So this is dx square. So this dx, it's a set produces this symmetry between even forms and odd forms. So for every eigenvalue, non-zero eigenvalue in the even forms, you have a non-zero eigenvalue in the odd forms. So you can naturally pair them. And what I currently think is natural thing to do is to take one of these eigenvectors as position and the other one as velocity. And so we have then kind of a natural kind of time t map. Sometimes called supersymmetry, but supersymmetry is out of fashion because it seems to work in nature. So, but what we have is a McKean-Singer symmetry is kind of for every so it implies that the supertrace of e to the minus L minus doesn't matter in the discrete is the other characteristic of G. For all T. So that's actually just the supertrace of 1. So we just take the number of even forms minus the number of even simplices minus the number of odd simplices. That's a very beautiful formula. I learned that as a grad student from the book of Seiken, Fröse, Kirsch, and Simon. Very beautiful book when I learned about discrete Schrödinger operators, which was kind of interest to me because it was related to chaos theory, problem of Lyapunov exponents for symplectic maps, like the standard map, or higher dimensional maps, which is completely open problem. Also symplectic geometry, but kind of a more ergodic theory. And also for so we can choose U0 and U prime 0. We can take these as eigenfunctions. Lambda, because it appears in pair, and then we have a psi is equal to U0 plus minus IB minus 1 U prime 0. This is then kind of plays the role of a complex wave. What it means is that if you have a solution of the wave equation, also here for this kind of Hamiltonian flow, then it actually has to give a complex solution, which is very, very nice. I like this kind of thing because we are here really in completely uncharted territory. So is there a discrete analog? I don't know, but let's look at a scenario. That would be the analog. So we don't have really trajectories of a Hamiltonian systems, but we have waves which close up after the same thing. And this is actually a spectral problem. So because of that, it's kind of natural to have this paired up, and so not to have to worry about both initial position and initial velocity kind of treated but the spectral problem is like that. So we have for L, this is Hodge. We have here B eigenvalues, B0 eigenvalues. Only two harmonic forms. So what we want is that these eigenvalues become non-zero and they stay the same, so that the period also of the thing stays the same. I don't think that this works in general, so you have to probably make some conditions on Ix, maybe have it compatible with a exterior algebra, all kind of things, like, so that it's kind of mimicking more the continuum. Maybe even you have to actually have the graph, maybe has to have something kind of more resembling a symplectic manifold, have even dimension, and things like that. So it could be that there are some conditions which have to be satisfied. But then if that would be true, you would actually kind of have in the limit, in a continuum limit, like in the barycentric limit, you would actually get to the Arnold, to the classical Arnold questions. But just because the classical Arnold questions are very hard, they need all these frameworks which has been developed, particularly by Fleur. You have to you can expect that this is also can also be difficult in the discrete. On the other hand, what you see is in the discrete, like for example the Lefschetz fixed point theorem, 3 lines of proof for a thing which is very complex in the continuum. You don't have to worry about that the fixed points are isolated. So this is in the discrete. You don't have to worry about kind of degeneracy. So that's kind of something which gives a little bit of hope. So maybe if there is something which is holding for all graphs, then it's usually easier to prove than if you have to kind of restrict your type of graphs. So that was my rant about this symplectic geometry. I will certainly come back to this at some point, not in the near future, but I keep thinking about this thing. So this was 3 years ago. We will see. Cool. That's it for today.